Hello friends, welcome to Power Electronics. Today we will discuss the single phase full wave midpoint converter using the center tapped transformer. So this is the diagram of a single phase full wave midpoint converter with center tapped transformer. This is the primary and this is the secondary winding. The secondary winding has two thyristors T1 and T2, also connected with the load RL. Here N is the midpoint of the secondary winding. If you look at the polarity, A is positive with respect to B. Also, if we take the N as the midpoint, then A is positive with respect to N and N is positive with respect to B. So we can see that VAN is equal to VNB, or we can say that VAN is equal to minus VBN. So here in the diagram, we have taken two assumptions. First assumption is that load current is continuous. Here our load current is continuous. Second, the transformer ratio is 1:1. So you can see this much simplified way in figure B, where we have given the supply voltage VAN and also VBN with the thyristor T1 and thyristor T2 and load is connected across it. So we will discuss this in detail. As you can see in the diagram as the source voltage, here this is VAN. Also the negative cycle, that is VBN. Also VBN is equal to minus of VAN. So here the thyristor is triggered by the delay of angle alpha. So from here, this point, the thyristor starts conducting at the instant pi. So if you look at here, when the positive supply is given to thyristor T1, the thyristor T1 starts conducting. But in the second, here the negative is applied to the thyristor T2. So the thyristor T2 is not working, it acts as a open circuit. So the thyristor T1 will conduct at the instant pi plus alpha. It is not conducting up to pi, it is conducting upon pi plus alpha. The reason is because of inductor. Inductor does not allow sudden change in the current, so it will reach at this point. Also, if you look at the load current here rises and it is not stopped at the instant pi. It starts conducting, thyristor T1 still conducting at pi plus alpha. This is the instant of alpha, this is pi plus alpha. Same we can also see in the VBN, that is thyristor starts conducting, it do not stop at the instant pi, it starts at the stop at the 2 pi plus alpha. Same it repeats, same as with the load current. T1 conducts in the positive half cycle. When A is positive, then the T1 conducts. When the supply changes, the B gets positive and A gets here negative. So thyristor T2 starts conducting. Here the thyristor T2 starts conducting and this thyristor gets off, that it acts like a open circuit. If you look at the voltage across thyristor T1 after a finding angle of alpha, here it is short. Why? The thyristor T1 is conducting. If you look at the thyristor T2 at that particular instant of time, you can see a negative voltage appear across it. It is not Vm, it is minus 2 of Vm. As we have already discussed in the class that VAN is equal to VNB. So if we took VAN collectively, we will get here the value that VAN is equal to Vm sine omega t, where here VBN is equal to minus of VNB equal to minus Vm sine omega t. So if we collectively add A and B, what we get is minus 2 Vm sine omega t. So this minus 2 Vm sine omega t appears across it. So with the voltage minus 2 Vm, the thyristor T2 is not in the conducting mode. It acts like a open circuit. So it is turned off by the voltage supply minus 2 Vm sine omega t. Same we can see in the next cycle. Here now the thyristor Vt1 stops conducting. The voltage across it is minus 2 Vm sine alpha, and the thyristor T2 starts conducting. Same process repeats again and again. So at the instant alpha, here at the instant alpha, the T1 is triggered. SCR T2 is in the reverse voltage, that is VAB is equal to 2 Vm sine alpha. As the current is transferred from T2 to here, from T2 to T1. Here you can see which has fall down sometimes, which has fallen down. You can see start from here, then it starts conducting T1. This is basically T2. T2 was already conducting. We have seen the graph from here, but here after that T2 was still conducting. Then the T1 again starts. So it is clear that this is T2. So current is transferred from T2 here to T1, and as a result T2 is turned off. Why T2 is turned off? Because the supply has changed its polarity. The magnitude of reverse voltage across T2 is obtained by applying the KVL. So if we apply here KVL, it is, this one was opened, it is Vt2 minus Vbn plus Van minus Vt1 equal to 0. So we will get here Vt2 equal to Vbn minus Van plus Vt1. This is the voltage we get across the V2. With T1 conducting, as the T1 is conducting, so that Vt1 is equal to 0. Therefore voltage across T2 at the instant omega t equal to alpha is given by Vt2 equal to minus 2 Vm sine alpha. This I have already discussed. Also the conduction time Tc of time provided by the circuit to the SCR T2 is given by pi minus alpha upon omega second. You can see here that when it is off, what you will get here, pi, here pi minus alpha upon omega. So what we get the output waveform here, if we will discuss the output waveform V naught, that it is 1 upon pi alpha to pi plus alpha, the point where the thyristor will conduct from alpha to pi plus alpha. So it is from alpha plus pi Vm sine omega t d omega t. So what we get the result here, 2 Vm pi cos alpha. So this is the average output voltage we get. The circuit turn off time is called as Tc. Tc is called as the circuit turn off time. And Tq, what we called as Tq, is the SCR turn off time. Tc is called circuit turn off time and Tq is called as SCR turn off time, as given in the specification sheet. Here the turn off time of the thyristor is more than the circuit turn off time, because ultimately we have to protect the thyristor. So it should be greater than the circuit turn off time. If here the condition occurs that the turn off time of the SCR is higher, then the commutation failure will occur and the whole secondary winding will be the short-circuited during the commutation failure. If the rise of fault current is higher, the incoming SCR may damaged in case the protective element do not clear the fault. This reveals that SCR is subjected to minus 2 Vm. So what are the following observations we conclude from this? We first conclude that when commutation of SCR is desired, it must be reverse biased and the incoming SCR must be forward biased. That means T2 got reverse biased and then T1 starts conducting. Then T1 gets reverse biased, then T2 starts conducting. When incoming SCR is gated on, current is transferred from outgoing SCR to incoming SCR. The circuit turn off time must be greater than the SCR turn off time. The circuit turn off time must be greater than the SCR turn off time, because circuit should turn off fastly than the SCR to prevent the SCR from the damage. As I already discussed that due to the commutation failure, if the rate of rise of fault current is higher, the incoming SCR may get damaged in case of protecting element do not clear the fault. So this is its explanation. Thank you very much.